No, not 10A. 10A, what were we talking about? Parametric and vectors. Parametric and vectors. Do we have some Endeavor cards of parametric and vectors?
Yes.
Yes. One of them is from a long time ago, derivatives with parametric. How do I find dy dx if I have x of t and y of t?
dy dt.
Good. dy dt over dx dt. How do I find the second derivative?
There's a formula.
There's a formula. I take the derivative of the first derivative over dx dt again. The derivative of the derivative over dx dt again. How do I find speed of a vector, or of an expression that's given in parametric equations? How do I find speed?
dy
Absolute
Magnitude of the
position.
velocity,
which
is the square root of x prime squared plus y prime squared.
Yeah.
Uh-oh, do we have formulas to study for tomorrow?
Yes.
Yes, we have formulas to study for tomorrow.
We know the vectors.
Well, since people didn't know how to answer speed, square root of x prime squared plus y prime squared, I'm kind of scared. Does that make sense? So we need to study our formulas, because speed is square root of x prime squared plus y prime squared. Right?
So do you want it in that form and not the dy over dx form? Where it's like dy over dt over dx over dt, so you find dy over dx.
Well, problem is speed isn't that.
Okay, I got you.
Speed is the magnitude of the vector, and the magnitude of the vector is found by Pythagorean theorem. Does that make sense? And that's why this card is so important, because speed is magnitude, and magnitude is, you have x prime, you have y prime, I need hypotenuse. So speed is magnitude, yeah. I have to take square root of x prime squared plus y prime squared. So I know that we know that normally in linear, speed is just the absolute value of velocity, but the problem is that's when I'm going linear. When I'm going with parametric, when I'm going horizontal and vertical at the same time, I'm going diagonal in a sense. Speed is not just the absolute value of velocity. Speed is, which technically, absolute value of velocity was a magnitude also, but it was easier because it was just a straight line. Now I have the hypotenuse of a triangle, so I need Pythagorean. Okay, guys, study those endeavors, even though we didn't have a quiz. We are on polar. Polar has a derivative, dy d theta over dx d theta, but I need to find y and x before I can do that. But now we're on area. We need to figure this out today, okay? So, areas, this is what we wrote down at the end of yesterday. At the end of yesterday. The Endeavor card, I didn't actually number it, but I would say it's an Endeavor card. How to find the area of a polar curve. Endeavor number, what are we on? 33. Thanks, Layla. Endeavor number 33 says, how do I find area between the pole and a polar? Like we saw yesterday, you guys remember how it went out and it was like area, 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 area. What are they doing? They're doing sectors. They're not doing rectangles. They're not doing the normal way because it's in polar mode. So we're doing sectors, sector, sector. The integral is finding areas of sectors. So I have to think, in a sense, kind of, wait, do I want to use this? Yes. Volumes of cross-sections, volumes of solids formed by cross-sectional slices. Cross-sections, I'm doing cross-sections, so this is different. That's three-dimensional, this is two-dimensional. But when I'm doing a volume, I take an area formula and I multiply it by depth to make it three-dimensional, but the integral makes the depth get infinitesimally thin to make my slices infinitesimally thin and puts them all together. That's kind of what it's doing here, except instead of the third dimension, I'm using the area formula, but I'm taking one of the variables of the area formula and making it the increment, making it the differential. So the change in theta could be really big, could be really small, but I'm making it d theta because then the integral makes these infinitesimally thin. When it makes it infinitesimally thin, then it puts it all together and it finds the area for me over a certain interval. But the interval, remember yesterday, the interval a to b isn't like x's and y's. Do you guys remember what are the bounds in my integral? What does a and b stand for? What kinds of values?
0.
Yeah, theta, right? So it's going to be like theta 1 to theta 2. So then what we're writing down for our hints is how do we figure out theta 1, theta 2? 1/2 function squared is just how I, times d theta, is just how I do it. So that's our formula. That's how I find the area between a polar graph and the pole. I need theta 1 to theta 2 of 1/2 function of theta squared. But I need to figure out how to plug it in, and that's where it gets a little tricky. So to find bounds, well, there's all kinds of different hints. Period, knowing the period of the graph helps because then we know when to start, when to stop. We saw yesterday some had periods of pi, only took pi to go all the way around. Some had periods of 2 pi, took all 2 pi to go around, and I need to know that in order to be able to solve. We're going to use a trick of going in function mode. You'll see how that works, and then we'll figure out our bounds. So let's start with an example. I think this is in your notes, right? Example number 3. Is this in your notes?
Did you want us to do that? Did you want us to copy the defined bounds for areas?
Oh, in your notes. Yeah. Did you guys not copy that yesterday?
Oh,
I didn't. I thought I had it longer. I'm sorry. Okay, a couple more seconds. I would write these down because this is how I'm going to approach problems today. Oh, your polar curves. I forgot. Making a pre-calc test for today. Your polar curves. I will email you. I think during period 5 I can email you.
Is the test with calculator or no calculator?
With calculator.
all of it or just some of it?
I think for tomorrow, all of it, but definitely during the AP review we'll do some of that.
Okay.
For tomorrow, probably all of it with their calculator, but if it's like a multiple choice, if it's a decimal, they'd say, sure, use your calculator. If it's not a decimal, they'd say, just be careful. Okay, we'll give you a couple more seconds. I forgot to fill it in. Is there anything else I didn't fill in? There we go. Finding zeros. Finding zeros. Because normally when we find zeros, we set y equal to 0, but now since it's polar, we're setting r equal to 0. So instead of seeing x-intercepts when we find zeros in polar, we are finding where it's actually at the pole, right? Example number 3. There's a couple dilemmas with it. Do we almost have a couple more seconds? You guys start looking at example 3. Let me turn on a light. I'll give you a couple seconds. Start looking at example number 3. A picture is going to help. Not that you always have to find a picture, but a picture is definitely going to help in this one. So I'm going to start there. I'm also going to kind of use some of our graphing techniques that we looked at, that we started using yesterday when we were graphing in polar also. Ugh, air turn on. Yuckies in here. Okay, here we go. All right. They tell me it's a cardioid. That's nice of them. I see this dependent on cosine, so I might be able to make some quick deductions from that. Kiddos, if I was to want to get the graph, if you could use your graphing calculator, I know you could plug it in and probably get a pretty good picture, but just in case you couldn't, we could, like we've been doing, plug in theta values and find r values and just kind of start sketching a bit. For instance, I'm thinking of cosine. Cosine always start at 0, right? At 0, cosine is 1. 1 plus 1 is 2. 2 times 2 is 4. Okay? So at 0, where is my cardioid going to be?
4.
Good. Now hold on, think about cosine for a second. What does cosine go in between? Cosine values. How high, how low does normal cosine go? 1 and -1. So wait, we just plugged in the maximum, right?
Yes, 4 and negative.
So therefore, can it go any bigger than 4?
Yes.
Can it?
No.
No, it can't go any bigger than 4, right? So I'm going to say I know the size of my graph. Can't go any bigger than 4. Doesn't mean it'll always be 4. Okay, I could go another round, right? What if I was to plug in
2.
pi over 2? So if we plug in pi over 2, what's cosine?
2.
Cosine is 0, right? So 0 plus 1, it'll be 2. So at pi over 2, I'm at 2. Keep going. What if I'm at pi? What's cosine?
Negative 4.
-1. -1 plus 1 is 0. 0 times anything is 0. Wait, so at pi it's here? And then we could keep going a little bit more. We could do like 3 pi over 2. 3 pi over 2, cosine is 0. 0 is 2 again. Now it's over here. And then we could plug in 2 pi, but at 2 pi it's going to be 4 again. Huh. What picture is this? It's like cardioid. Cardioid is kind of like a heart, right? It has a little cusp. Technically, we could we plug in pi over 4? Yes, and if we plug in pi over 4, just a hint, pi over 4 is yucky. What's a good cosine value? Pi over 3, right? Let's plug in pi over 3. So if we were to plug in 3, that'd be 1/2. 1 plus 1/2 is 3/2. 3/2 times is, 3. Remember, it's a radius. That's why I go circle. If I was to plug in so 2 pi over 3. -1/2. 1 plus -1/2 is 1/2. 1/2 times 2 is 1. It's only 1? Oh, it's right there. Huh. What's going on? Oh, so what's it going to do on the other side since it's symmetric? That's ugly. Hold on. Undo. Ugly. So I'll do this pi over 3. And I'll do this pi over 3. Make it pretty. Well, I said tomorrow you get to use your calculators, right? Still ugly. But they could expect you to be able to, yes. Which, once again, you could just make a quick table and then figure it out, or you could memorize. Okay, give up. Whatever. There it is. We're done. Okay. Blech. Let's think of another couple things that we could have done besides just graphing it, because we have it now. What are some of those? Oh, that's not what I wanted. That's not what I wanted either. Okay, I give up. The page before, didn't I say find zeros? Okay. What do I mean by finding zeros? I could set r equal to 0. Divided by 2, I get 0 equals 1 plus cosine theta. Cosine theta equals -1. And where does that happen? Negative pi? No, pi? 3 pi? 5 pi? How could that help? Well, I know that it doesn't hit right here until pi. That kind of helps. If I start to get the shape, then I know, okay, so pi is halfway. I just need to go 2 pi to go the whole way. Zeros, in this case, it wasn't all that exciting, but zeros could help it sometimes to know when it's at the pole. What's something else that I said that we could do? Find the period. How would I find the period? I guess at the argument. What's the argument? Argument is just theta. So set theta equal to 360 or 2 pi. But didn't my graph also tell me 2 pi would finish my graph? So you have a few different ways. One, you can figure out period by actually graphing. Another way, you can just actually set the argument and say, hey, I know that cosine, sine, any of those cycle, so it's going to cycle every 2 pi, etc., etc., etc. Kiddos, how would I find this area? Something in front, though. 1/2. What are my bounds if they're supposed to be thetas?
From 0 to 2 pi.
You could do 0 to 2 pi. And what would be inside?
And the radius square.
2 squared.
Why? I have to use my formula. My formula says 1/2 integral of f of theta squared, or f of theta is my r squared d theta. Now, what is this technically going to do, just so that you can visualize? What this is going to do is go from 0 to 2 pi. So it's going to say, hey, I'm starting to collect. I'm collecting. Little sectors, they're getting infinitesimally thin. Collecting. And then what's it going to do? Collect. So it's going to be a little different than you're used to. But it's going to start at 0 and it's going to start collecting. That's what the 0 to 2 pi does. But what's my job? Just solve the integral. Okay. How do I solve the integral? If you had to do it by hand, you'd have to plug and chug. If you didn't have to do it by hand, it'd be a little messy because I'd have 1/2 times the integral 0 to 2 pi of 4. Well, 4 can come out, right? So make that 4 over 2. And I have 1 plus 2 cosine theta plus cosine squared theta. Aw, stink. Come on. There we go. How do I integrate 1? Psh, easy. How do I integrate 2 cosine theta? Easy. How do I integrate? Aw, stink. What's wrong with cosine squared?
You can't do
I can integrate him. At the very end, I'm going to do from 0 to 2 pi, but how do I integrate cosine squared?
identities.
Uh-huh. How do I integrate cosine squared? 1 minus sine squared. I still have a squared. Stink.
Power of this.
U is cosine, du is sine. It's not there, but I can do power reducing, which tells me, oh, that's why they were important. What's cosine squared equal? 1?
1 minus sine.
Minus? No, no, 1.
Plus.
Plus what?
Sine.
Sine squared.
No. Power reducing. Not sine squared.
Sine 2. Sine 2.
1 plus sine 2 theta?
Uh,
Do you have
Power reducing formulas. I think it's cosine 2 theta, isn't it? I started a couple days ago. I'll go find it. It's back here somewhere.
it is cosine.
Cosine squared is 1 plus cosine 2 theta all over 2. Power reducing. That's the way that we have to solve a lot of these, guys. Because it's r squared and r's have cosines and sines. And so if we had to solve by hand, we would have to use the power reducing. 1 plus cosine of 2 theta all over 2 d theta. Then I'd be able to keep plugging and chugging. Now I'd end up with 2 times theta plus 2 sine theta. 1/2 would be plus 1/2 theta plus 1/2 cosine 2 theta. U is 2 theta. Du is 2, so that'd be 1/2. I already have du, so I'm good, I think, right? Yeah. So I would just have sine 2 theta. Thanks. And all of that from 0 to 2 pi.
Is it 2 sine?
I don't think so because
Or is it 1?
that'd be integral 0 to 2 pi of 1/2 plus 1/2 cosine 2 theta d theta. Let me zoom in because it's getting small. U would equal, for this one, U would equal 2 theta du. Sorry, we do this differently than I do it now. Du is equal to 2 theta d theta. No, 2 d theta. Oh dear.
So that'll be 1/4.
Oh, yeah, you're right. So then I can plug in 1/2 to u, and 1/2 times 1/2 would be 1/4. Thanks, Melissa. And then at the end of the day, blah, 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 what do we get down to? I think it's 6 pi. At the end. But that's how we would integrate if we needed to integrate. Huh?
Can I use a calculator like this?
I'm saying if you had to do by hand, which means sometimes you have to do by hand.
But no,
I did say that, but I probably shouldn't have said that. It was when we were doing integration. So when we were doing integration by parts, we were doing trig integration. Chapters 5 or 6, but it's in your endeavors, isn't it? I don't know why we need to look back in our notes, I don't think. Because it's in our endeavors how to use the power reducing. Tomorrow might have some by hand. I don't know if I can totally say no, because that would totally change the test. So you guys are trying to shortcut stuff now. Find the inside the smaller loop. Wait, what? Okay. What do you guys want to do? Find some zeros? Do you want to start graphing with a table? Do you want to just magically have it memorized and have all like 20 polar graphs, the limasomes and the cardioids and the inner loop and the non-inner loop and the circles and the ellipses and the roses and the landscapes all memorized? I don't know. I don't like that way. What do you guys think? Zeros or table? Zeros? Okay, so if we were to find our zeros first. So then cosine of theta is equal to -1/2. When does that happen? 2 pi over 3?
Yeah,
5 pi over 3? No. 4 pi over 3? Second quadrant, third quadrant? Unit circle importance? So what does that mean? That means that if I have my graph, if I have my curve at 2 pi over 3, it's going to be 0. And at 4 pi over 3, it's going to be 0. Well, that's something. Kiddos, if I have cosine, well, without us memorizing, I'm just going to go for it. If I start at 0, cosine is the maximum 1, right? So 1 times 2 plus 1 is 3. So I know it's going to go 1, 2, 3. 3 is going to be the highest it goes. So I could figure out my graph size. If I was to plug in pi over 2, cosine is 0, so 1. It's symmetric, so if it's 1 here, it's going to be 1 for 3 pi over 2 as well. If I wanted to plug in like pi over 3, because it's easy, 1/2 times 2 is 1, 1 plus 1 is 2. So I can say, okay, da-dun-da-dun-da-da. Wait a minute, it's supposed to hit 0 twice? Why? Because if I was to plug in pi, guys, if I plug in pi, what do I got? Cosine is -1. -1 times 2, -2, -2 plus 1, -1. Anytime you have an expression where it can go negative, it's going to backtrack. What do I mean? Well, at pi over 3, it hits here, but then at pi, where is it? Here. What? How did it get there? It looped-de-looped in itself. It has an inner loop. Do you see? Because it was going positive, 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 0, negative, 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 negative 1, then it goes negative, 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 positive, 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 positive. So it backtracked in itself. Guys, what area do they actually want? The whole thing? They want this one. Well, how do I get that one?
It's the whole minus, oh, so different bounds is between.
Different bounds. That's all I need is different bounds. I don't need to subtract anything. Because, guys, what theta starts the inner loop? Because then my integral says I can do between the curve and the pole. I can find that area. So what started it? 2 pi over 3. The 0 did. It hit the pole at 2 pi over 3, and then it hits the pole again when? 4 pi over 3. So then I can go ahead and say area is equal to 1/2 2 pi over 3. See why zeros can be nice? Zeros told me beginning and ending of the little baby loop. Huh? Otherwise, everything is going to be the same because I have my 2 cosine theta plus 1 squared d theta. I'm going to have to use power reducing again. Do you see why power reducing was started in this section?
Maybe.
For the bracket, is it always
Is it always what? Symmetric? Yeah. Yeah, always symmetric. So if I was trying to graph or solve, I'd have 1/2 integral 2 pi over 3, 4 pi over 3, 4 cosine squared theta plus 4 cosine theta plus 1 d theta. Trying to see if there's an easier way. Is there an easier way? No, not really. Then I could go ahead and say then I could say here's the problem. If you guys totally rely on calculator tomorrow, then you're going to have all these decimals that you have to check with all these exact answers with pies or with radicals or with this, that, and the other. Hence why I'm kind of giving you a warning about that. I'm going to have 2 cosine 2 theta, right? Plus 2 plus 1. So I could say 1/2. U is 2 theta, du is 2. I have it, so I'm good. So I end up with sine 2 theta plus 4 sine theta plus 3 theta from 2 pi over 3 to 4 pi over 3. And then I'm just going to do a dot, dot, dot at this point and say the final answer ends up being pi plus root 3 over 2 minus 2 root 3. I guess you could do something like, then that would be 1 root 3 over 2 minus 4 root 3 over 2, so minus 3 root 3 over 2. Is that right? 1 minus 4 would be negative 3. After you plug in and solve everything. But, kiddos, is there any other way, let me turn off the light, is there any other way to do this besides 2 pi over 3 to 4 pi over 3? Probably. What's true about this polar curve? Is he symmetric?
Yeah.
So could I theoretically have doubled?
Yes.
have doubled them and cut them off early, where would I have cut them off instead of 2 pi over 3 and 4 pi over 3? I could have said 2 pi over 3 to, what's halfway in between? Pi. Because 2 pi over 3? 4 pi over 3? What's halfway in between? And what's this angle? Pi. So the other way that you could have done it, I'm just going to put a little or. Or you could have done double 2 pi over 3 to pi. Why might that have been nice? It might have been easier to plug in a little bit, because plugging in pi, cosine is just, well, cosine is -1, but sine is 0. So it could have been easier in plugging in if you had just gone from 2 pi over 3 to pi and then doubled it, because then you would have had just the bottom half, and then double it, you would have had the top half. Oh, these two? Well, 2 pi over 3 came from my first 0, right? It was the first time when it hit was at 2 pi over 3. Pi is when it goes halfway. Pi is -1. So 2 pi over 3 to pi, in essence what you would do in this one is you would take your little, that's really dramatic, but you would just find this, and then you would double it to get the top half too. Because when I'm graphing pi over 2, now I'm at 2 pi over 3, now I'm at pi, now I'm at 4 pi over 3, and then I keep going up. Does that kind of make sense? Kind of, sort of, maybe. Melissa, do you have a question? Oh. Okay, a couple more seconds on him. Do we have another example? Let's skip ahead to example 6. I'm not going to solve him all the way through. I'm not going to solve him by hand at all. I just want to see if we can figure out how to do him, how to set him up, okay? At this point, I'm just going to write integrals, no more solving by hand. All right, so in example number 6, give an expression for the total area enclosed by the polar curve r equals sine squared. Now, you could memorize sine squared, or you could say, whatever, I got this. We could find our zeros, just in case that's helpful. Well, hold on. When is sine 0? Well, it starts at 0, right? So 0, pi, 2 pi, etc., etc., etc. Okay. If I was like, that's not enough, I don't know what it looks like. Okay. We could do our theta and our r. If I was to plug in 0, I already know 0. If I was to plug in, what's a nice one for sine? Pi over 6? Pi over 6 would give me 1/2. 1/2 squared is 1/4. Pi over 2, sine is 1. 1 squared is 1, right? I could do 5 pi over 6. And I have -1/2. -1/2 squared is, or 1/4 again. At pi, I have 0. You keep on going, always staying positive. If it's always staying positive, okay, it starts at 0 at 0. At pi over 4. It's going to be (1/4). At pi over 2, it's going to be 1. Over here, it's going to be at pi over 6 again. Sorry, pi over 6. I did pi over 4. Pi over 6 is down here. 1/4. At 5 pi over 6, 1/4 again. And then 0 again. So far I have this. Now what's going to happen as I keep going? Well, if I go to 7 pi over 6, -1/2 squared, still 1/4. So 7 pi over 6 is still going to be 1/4. And then 3 pi over 2 is -1 squared, which is still going to be +1. And then 11 pi over 6 is still going to be 1/4. So I have this. And then I have this. That's my curve. Or a question, kiddos. What's my period? Set the argument. Equal to? How long does it take to complete a period? Oh. It's not sine squared of 2 theta or sine squared of 3 theta. When my period will get messed up, it's just sine squared of theta. So it'll take 2 pi to complete. So I don't even have to think that hard on this one, guys. Yes, the picture helps, but at the same time, if the period is 2 pi, and if I want the whole thing, then what am I going to put in my integral? Yeah, 0 to 2 pi of my sine squared squared. Sine squared squared. And this one would be messy to do by hand, but you would have to do power reducing twice. Because you'd have to say 1 minus cosine 2 theta over 2 squared, and then square it all out, and then plug in again. That's why we're not doing it by hand for sure. But final area would equal, I think on this one, 3/8 pi. But guys, we need to get to what happens when we find area between. This is the end of the notes for 10b. What happens when we need to find area between? Area of picture helps, but maybe we can figure out sometimes a different way. When they ask things like inner loops, that gets a little tricky. But area between, we're still going to have area between, but with polar, let me zoom in, still subtraction. Still subtraction. But angles might be different. Angles might be different. Kiddos, looking at time and the way it is, I need to have a quick discussion with you. We haven't gotten to the hardest examples. And we could have a quiz tomorrow, however, I don't think we're ready. Layla's not going to be here Friday. Layla can come on Friday.
JK guy.
I think we should push it till Friday. But is there anyone who for sure is going to be gone Friday? Because if you take it the Monday after we get back, grades will plummet. So right now, I need eyes on me. I need a commitment with a thumbs up. Yes, I'm going to be here Friday so we can have another day to work and review and answer questions. Give me a thumbs up if you're going to be here on Friday. Be here on Friday. Okay, test is Friday. Test is Friday, so we can keep practicing.
Thank you.
Mm-hmm. Thank you for committing to be here. That's why I was scared that this people were not here.
I came today just for the math class.
I'm so proud.
I'm
So
terribly
proud.
sick. What is that?
No, so
She's
proud.
not gonna tell me.
No, what is it? What is it?
Which one?
The right after subtracting, it's a 1/2 from.
Alpha to beta. You can
Yeah,
say
alpha
theta
to
1 to
beta.
theta 2 is 1, or alpha to beta.
She's not gonna tell me.
one is infinity? No.
No, it's
No,
it's
alpha. It's a little alpha. It basically means theta 1.
Theta 1.
You can say theta 1, theta 2. It's still just as good. Theta 1, theta 2, guys, is just as good.
Is this the over?
Yep.
34?
Yes. Endeavor 34. So you can see a few different wordings, right?
Is homework due on Friday?
Yeah.
Homework is every day,
packet?
right?
Oh, you mean the actual, yeah. Yeah. I'll just say chapter 10, homework, and test. Well, someone might, but
It'll probably
I
be
don't
me.
think they do.
It'll probably be me.
Okay, Melissa might judge.
I drove like something else.
Yes.
Hey!
Or
Something light and fluffy. There's an amendment
and it was signed.
by both parties?
No, it will be right now.
Oh, okay.
After class.
All right, can I scroll down so you guys can see what I put to it? To find bounds, find intersections. La 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 la. To find bounds, find intersections. But we're used to that, right? Whenever we were doing area between, we would set two functions, y equals, I don't know, x squared and y equals x. We would set them equal to each other and say, okay, intersections, and we say, okay, bounds. We have to be careful, though. We have to be very, very, very careful with our bounds. Yes, we're going to set them equal to each other. Yes, we're going to figure out where they cross paths, but we have to keep in mind two things. As you saw on the card, outer versus inner. Which one's which? Which one goes where? Outer versus inner, especially important for area between. Especially important for area between. And then we're gonna have to use our graphs. The nice thing is that they make it really tricky. The AP guys usually give you the graph, which is nice, but we're still gonna have to use the graphs, and we're gonna have to watch the movement, because polar curves, if you look at the graph, you don't know when it was somewhere, you just know that it was there. To know when, you have to know the angles, and that's where it gets tricky. To know when, you have to know the angles, and that gets tricky. Can I go to an example real fast, since we only have a couple minutes? Okay, let's go here. All right.
Should we copy this one?
Example number 5. I skipped it because it was an area between. Move this out for just a second. Area between. Now, kiddos, they could give us different ones, but this one says that lies inside the circle, and we started talking about this the other day, and we couldn't do it. We got stuck. The area of the region that lies inside the circle and outside the cardioid. Inside the circle and outside the cardioid. Now we figured out, hey, it's an area. Hey, there's theta bounds, but we just figured out this just got a lot more complicated. Area between. Okay. I know that when, I'm going to put my little yellow marks back, when I'm thinking about this area, guys, if I go to the circle, if I go all the way to the circle, is that good? Well, it's good, but is it perfect?
No.
It's going to cover area that I don't want. So I'm going to have going all the way to the circle, but what else do I need?
Yeah.
Subtracting going to the cardioid. Does that make sense? I'm going to go to my circle, I'm going to go to my cardioid, and I'm going to subtract the two. But what do I need to figure out? I need to figure out for what angles I can use these two, right? So how do I figure out for what angles? Well, first of all, I can think about a couple things. First of all, I have the circle r equals 1. I have the other r, 1 minus cosine theta. I could think about my intersections, because usually those are helpful, where my r's and thetas are the same. And if I set 1 equal to r1, r2, I'm going to end up with cosine of theta equals 0. Well, when is that true? Well, that's true when theta is equal to pi over 2, 3 pi over 2, etc., etc., etc. Do you see those intersections reflected in the graph? Yes. Yes, we do. Okay? Those intersections are reflected in the graph. Now, question, what else do I know? What else do I need to know? If I go from pi over 2, guys, you saw these graphs a second ago. If I go from pi over 2 to 3 pi over 2, am I going the right way? No. So I can't go from pi over 2 to 3 pi over 2, but I can go from negative pi over 2 to pi over 2 of the bigger one minus the smaller one. Layla, can you just see who's calling?
Say student speaking.
You can just look at the name.
Nora.
Okay, I'll call her back. Thanks. All right, cool kids. Anyway, you would plug in what would be my outer radius, the circle, so that would be 1 d theta, 1 squared d theta, and what would be my inner radius? My cardioid. All right, cool kids, get out of here. We need to think about the outer and the inner and the intersections tomorrow we'll see, I don't know if we'll do, we might wait till after break to see how the AP guys can make it this much harder or that much harder, but that wouldn't be required for test on Friday. Alright guys, work on worksheets tonight. If you have questions, I'll be here after school today. Sorry to keep you a little bit longer. Huh? Common is what they both have inside. Yeah, common is what they both have inside. So this one, because this one, what's both inside, not this,
Here.
this.
Yeah, it's here.
That's common inside. Yeah.